Hello, I hope you're doing well. In this video on antiderivatives, I want to show you a connection between area and antiderivative. We're going to do this by using a linear motion problem. So let me get started here. Sorry about that. So let's do a small linear motion problem, and then I want to show you how it connects to a graph. So my claim is that the total distance traveled of this particle is going to be equal to the area of the velocity graph. So let's get started. Suppose I have a particle, it travels in a straight line, and I know that the acceleration is -2. The initial velocity is 8 feet per second, and the initial displacement is 4 feet. How do I compute the velocity function? Taking the antiderivative of -2, I get -2t. My initial condition 8 yields -2t plus 8. Figuring out the displacement function, I take the antiderivative of -2t plus 8, and I get -t squared plus 8t plus, well, when I do my calculations, I get a 4 for my constant. So how do I figure out the total distance traveled? And I'm going to pick two numbers here. I want the total distance traveled between 0 and 6. In other words, for the first 6 seconds of motion. I'm going to draw a number line. This is going to be my velocity line. I know my velocity is equal to 0 at t equals 4. Well, what makes the velocity equal to 0? -2 times 4 plus 8. Well, that is 0. That's how I figured out this 4. I skipped a little calculation here. Plug in a test value between 0 and 4. I'm going to pick t equals 1. T equals 1 gets me a positive answer for velocity. That means between 0 and 4, my particle is moving forwards. I'm going to call this leg 1 of the trip. Now for leg 2 of the trip, between 4 and 6, I get a negative value here. The reason why is I'm going to pick a test value between 4 and 6. Let's say 5. -2 times 5 plus 8, that's a negative number. So therefore, my particle is moving backwards. I'm going to call this leg 2 of the trip. So in leg 1 of the trip, I start at t equals 0, and I end at t equals 4. But my starting positions are 4 and 20. Now, how do I get that? Well, I plug in 0 and I plug in 4 into my position function. Plugging in 0 gets me a 4. Plugging in a 4 gets me a 20. So my total distance traveled is position 20 minus position 4, or a total of 16 feet. Now leg 2. I start at t equals 4, it ends at t equals 6. So that means my position is 20 and my end is 16. If I plug 6 into here, I believe we get 16, unless I did some arithmetic wrong. So my total distance traveled is final minus initial. In other words, my ending position minus my starting position. But since I'm talking about distance, I want to take absolute value of it, and I wind up getting 4. So my total distance traveled is 16 plus 4, or 20 feet in the first 6 seconds. I want you to keep in mind that these two numbers, 16 and 4. I claim there's a relationship between 16 and 4 and the 20 and the area of the velocity graph. So let me plot the velocity graph here. Well, the velocity graph, when I look at this is a linear function. That's nice. So it's a straight line. Has slope of -2 and an intercept of 8. So I have an intercept of 8, and I know this crosses the t-axis at t equals 4. And so that's what I'm representing here with this little picture. Now this is a nice picture to compute area. I have this region right here. What is the area of that region? Well, it's a triangle, so it's 1/2 base times height. Let's go to the triangle to figure out some numbers. My base is 4, and my height is 8. So I get 1/2 4 times 8, or 16. 16. I've seen that before. That's the first leg of the trip. So this area here is the same answer as this calculation up here. What about the area of, well, let me put in a little dotted line here, of this triangle? Well, again, it's 1/2 base times height. My base is 2, and my height is 4. My base is 2, and my height is 4, and I get a total of 4. That's exactly what length 2 was. So let me just go back ever so slightly. I talked about, in the very beginning, feet per second and feet. So this, or these numbers, have units of feet. What about these? Well, base times height. What are the units for the base? Well, the base is in this direction. So this is in seconds. What about the units for the height? Well, the height is in this direction, this vertical direction. Huh. That's a velocity. So this is in feet per second. What about area? Well, area is equal to 1/2 base times height. Well, let's look at these units together. Well, 1/2, that's unitless. That's just a factor. The units for the base times the units for the height, seconds divided by seconds, gets me feet. So this may seem really odd. This area for this first triangle has an area of 16 feet. Yes, an area of 16 feet. I am not saying that incorrectly. The units for this has an area, or sorry, the units is feet. So the area of this second triangle is 4 feet, not 4 feet squared, but in this context, our area measurement is feet. So this is a small connection between antiderivatives. I computed these numbers for the 20, the 20, and the 16 using the position function. The position function was an antiderivative of velocity. Antiderivatives are connected to areas. And I think that's an amazing thing. I hope this video, this small connection, is useful. I know it's going to become very useful in later videos. So if you have any questions, let me know. Have a great day. Bye.